My name is Margarida and I am a first-year PhD student at Carnegie Mellon University in Técnico Lisboa. Today I'm presenting our paper, Counterfeiting Congestion Control Algorithms. Congestion control algorithms, or CCAs for short, determine important properties of the Internet, such as whether or not competing applications share network bandwidth fairly, how stable bandwidth allocations are, and whether network links are utilized efficiently. These and other properties of CCAs are a topic of active study for researchers in the networking community, and we know companies have deployed CCAs in the past that didn't satisfy these properties. 2 years ago, researchers found that Google's CCA BBR was not fair, so devices accessing Google would take up more of the bandwidth than their fair share. Researchers were able to perform this kind of analysis because Google CCA is open source. However, with new applications, a lot of new algorithms are being used in the Internet, and some of these algorithms are proprietary, which prevents us from performing the same kind of in-depth analysis we can perform on open-source CCAs. For example, last summer, researchers at CMU analyzed the CCAs being used by 3 different video game engines and concluded that these proprietary CCAs do not fit any previously known algorithms. Because these CCAs are closed source, the insights they were able to get were limited, so how can we hope to analyze properties of unknown CCAs if the companies don't release them? Our goal is to reverse engineer CCAs, so more in-depth analysis can be performed on closed-source algorithms. And we propose to do that using a technique commonly used in the programming languages community, called program synthesis. The goal of program synthesis is, given a set of input values and the output for each one, figuring out the function or program that will produce the corresponding output for each input. To do so, we feed the input-output pairs to a synthesizer, and the synthesizer will return a function that will produce a desired output for each input. Our goal is to use program synthesis to reverse engineer a CCA. To do that, we consider the same input-output structure for the CCA. The CCA's input are network signals that tell us the conditions of the network at any given time, such as ACK and send packets, the maximum segment size, or the round-trip time. Besides the network signals, the CCA also considers its current state as input, and the CCA state includes values such as the congestion window size and the slow start threshold. The output of the CCA is then the new CCA state. Unfortunately, we cannot obtain the clean input-output examples that we had for F in the previous program synthesis example. So our goal is to synthesize CCAs from network traces, which I'll explain later in this talk. For now, let's focus on the CCA we are synthesizing. The code that implements CCAs on the Linux kernel looks like this, which is a lot of code to synthesize. Fortunately, to define a new CCA, only a small portion of this code is re-implemented, so we focus our synthesis on this portion of the code, to which we call event handlers, and the remaining boilerplate code stays fixed. So instead of synthesizing all the CCA code, we move the boilerplate code to the input side and synthesize only the event handlers. In this paper, we take the first step towards CCA synthesis. We focus on synthesizing only a simplified version of Reno. In our simplified Reno, we consider the state to be just a congestion window, and we consider 2 event handlers. WinACK is the function that increases the window size when the CCA registers an ACK, and WinTimeout is the function that decreases the window size when a packet times out. We want to synthesize WinACK and WinTimeout from the information in the network traces. The network traces are timestamped records of what the CCA sees in the network. In which timestamp, we know which packets were ACKed and which packets were sent, so in practice we know which packets are in flight at any given moment. We want to synthesize the handler functions for the CCA. We have part of the inputs from the trace, but we are missing the previous congestion window on the inputs, and we are missing the output congestion window as well. The missing information, fortunately, does not prevent us from doing synthesis, because we do know something about the congestion window values that we are missing. Each timestep's input is the previous timestep's output. For example, the input window on timestep 1 is the output window on timestep 0. So the problem of CCA synthesis, we don't have examples for each independent execution of the desired function f. Instead, we have information about the successive composition of the functions we are trying to synthesize. This makes CCAs a more challenging synthesis problem. Now that we have our formulation, we could try to apply a basic naive program synthesis method to the CCA domain. We start by enumerating candidate functions for the CCA handlers using the inputs and additional variables. Then we use an SMT solver, such as Z3, to answer the query, are there functions of this shape that fit all our collected network traces? If the solver answers no, then these candidate functions do not fit the traces and we move on to the next set of candidate functions. And we enumerate functions until we can get a set that matches all our traces. We cannot apply this naive method directly to CCAs though. The reason for this is that our search space is very large. Even our very simple language, just expressive enough to synthesize Reno, allows for approximately 20,000 WinAC handlers, which when combined with 20,000 win timeout handlers would result in several 100 million possible CCAs. So even if each solver call just takes 1 second, this naive approach could take over 15 years to produce a CCA. In summary, CCA synthesis is more complex than the simple example with the F function I showed you in the beginning of this talk. So if you try to use existing techniques to synthesize a CCA, it will likely run forever and never return an answer. However, we found ways to overcome these challenges. We implemented our ideas on a prototype CCA synthesizer, Mr. 880. It's named after the movie Mr. 880 about a money counterfeiter that only ever counterfeited $1 bills. Our first goal is to synthesize the simplified version of Reno I showed you before, so we say Reno is our $1 bill. To make our search more tractable, we focus on 2 main goals for our synthesizer. First, we want to make simpler and faster solver calls. Second, we want to reduce the search space, which reflects on fewer solver calls. The first step we take towards achieving these goals is to separate the traces. First, we consider only the trace with the fewest time steps. We then use only this trace to ask the solver, is there a CCA that fits the trace? This is a much simpler solver call than if we were using all traces. From the solver, we get a set of handler functions that fits that one trace. And we move on to simulation, where we compare this CCA with all collected network traces. So in simulation, we ask, does this concrete set of handler functions fit all of our traces? This is a very fast query, because since we already have the concrete CCA functions, no reasoning is required. If it does not, we add the trace that failed to the set of solver traces and repeat the process. If the CCA already fits the traces, then we are done, and the synthesizer can simply return the CCA. To simplify solver calls even further, we synthesize each handler function separately. We start by considering just the part of the trace until just before the first packet times out. We ask the solver, is there a WinAC handler that fits this first part of the trace? This simplifies the solver's job because it does not need to reason about 2 handler functions at the same time. Once a WinAC function is found, we fix it, and we ask the solver for a timeout handler that fits the whole trace. Our second goal was to reduce the search space, thus reducing the number of calls to the solver. We use domain-specific knowledge to remove from the search space functions that we know would not be good handlers, even before considering the traces. For example, we remove any function whose output would not be in bytes. And similarly, we don't need to consider for WinAC handlers functions that can never increase the window size. Removing functions like this allows us to reduce the search space by around 80%. To summarize, to make CCA synthesis problem more tractable, we implemented some improvements in Mr. 880. We start our synthesis process considering only the shortest trace, and we synthesize one handler at a time. Together, these 2 ideas contribute to simpler solver calls. Besides, we use domain-specific knowledge to remove handlers from the search space, thus making fewer calls to the solver. We tested our approach in a few simple CCAs, including Reno, our $1 bill. The naive synthesis method that I showed you in the beginning did not synthesize Reno, it timed out after 1 day. With our optimizations, however, Mr. 880 was able to synthesize simplified Reno in 13 minutes on a MacBook. In conclusion, we are using program synthesis to reverse engineer CCAs. We have a working synthesizer, Mr. 880, that can reverse engineer Reno. In the future, we will focus on working on internet traces instead of simulator-generated traces, which comes down to making the synthesis robust to measurement errors. We will also expand our synthesizer to be able to counterfeit larger bills. or that is, more complex CCAs on the web. Thank you for listening to me.